Evening all. As promised over a year ago, here's the code to test the MC6821 using the PiC16F877A microcontroller manufactured by Microchip. Now here, at the very beginning, after the semicolon indicates remarks. I just like to put this little section here so that I know when I started the program and when I finished the program. And that way in 20 years I can look back and say, wow, I was pretty smart back then. So for the very beginning, we have to set the processor type. And we use this command right here, processor 16F877A. And right after that, we have to have the include file, the header file. And we use hashtag include, less than and greater than sign, and within that, P16F877A dot include. Next, we have to initialize the configuration bits for the PiC16F877. Now here, I have this top one remarked out because it's for a 4 megahertz clock, and I used a 20 megahertz clock, so this is the one that I'm actually using here on this second line. Notice the underscore. There's two underscore markings right here. It's underscore, underscore. Let's see if I can space those out and you'll see it. There you go. Underscore, underscore, config, and in binary, single quotes at the beginning, B single quote, ending in a single quote. I have 001101 00000010. Let me put this these two underscores back together. Don't forget that it's really confusing, even in the PDF, that they don't show two separate underscore markings. So this 00 and this 00, CP1, CP0, they're the code protection bits. And when they're set to 0, you have 00 here and 00 here, code protection is enabled. That means that when you download the code from your microchip using a programmer, for instance, the Top Max made by EE Tools, the code that is removed from that microcontroller is not usable. It will download all ones. If you don't want code protection enabled, set this 11 and set this 11. These 4 bits right here. And that will enable you to download the program using a programmer. In-circuit debugger is disabled if you set this bit to 1. This bit here is unused. Here we have flash memory is not writable by program if you set this bit to 0. Here EEPROM read protection is disabled if you set that bit to 1. Let me change that to 0. These are all remarks. So low voltage in-circuit programmer disabled. that means that port B, bit 3, is set to IO. That's this right here, this bit right here. Brownout reset disabled if we set that bit to 0. Power up timer enabled if we set this bit to 0. Watchdog timer disabled if we set that bit to 0. And here is where we select our 4 megahertz or 20 megahertz clock. So I have these two bits set to 1, 0, and so the 20 megahertz clock is selected. If I had a 4 megahertz clock, I'd set these two bits to 0, 1. That's your FOSC1 and FOSC0 bits of the configuration register. Moving along, we want to set these port bits to certain functions, and we'll use the hashtag define command. And what that does is, it's really neat. You can set, for instance here, port D bit 0, we're going to label it. And instead of writing port D bit 0 in the program to where I would forget what port D bit 0 is by the time I got to the end of the program, we can label port D bit 0 as start underscore switch, and port E bit 1 reset bar. These are all labels that you can create. You can name these port bits anything you wish with the hashtag define function. So port E bit 0 is read write bar. Port A bit 2, chip select 0. Port A bit 1, register select 1. Port A bit 0, register select 0. Port C bit 1, direction. Port C bit 0, G bar. The variables J, K, and L are used in delay counters. And I have those delay counters set at the end of the program as subroutines. But what is really nice about this section right here is the C block and NC commands. In the PIC16F877A, starting at address 20 hex, this is 0 little x 20. The 0 little x indicating that the value following is a hexadecimal value. But at 20 hex, we have some memory allocation that we can use to store variables. So J, K, and L. The variable J will be stored at 20 hex, K at 21 hex, and L at 22 hex. And we close out that section with NC. This makes it very easy to determine where your variables will be stored in memory. The reset vectors, org 0000 hex. The compiler needs to know where your program begins within that microcontroller, and that is what this command org accomplishes. So we are going to have our very beginning of the program start at 0 hexadecimal. Now we are going to initialize the PIC16F877A. Let me repair that remark. The first thing we want to do is we want to switch to bank 0. This is the bank that contains the registers for ports A, B, C, D, and E. In the olden days, we used to do this by setting the status bit RP1 and the status bit RP0 to 0. Bit clear file status RP1, bit clear file status RP0. But nowadays, and I've got that remarked out, so these two lines of code are not used in the program when it's compiled. But nowadays, we use the bank select command, and we will bank select port A, and that accomplishes the same function as these two remarked out lines of code. Now, when we have bank selected port A, I want to initialize ports A, B, C, D, and E data latches to zeros. So we clear file port A, clear file port B, clear file port C, clear file port D, and clear file port E, so that ports A, B, C, D, and E contain all lows, all zeros. Now we're going to set up the ports as inputs or outputs of the PIC16F877A. Port A, we want to set all bits as outputs. The first thing we have to do for port A, because it shares the A to D conversion inputs, we have to set port A as digital I/O. So we move the literal value of 6 hexadecimal to the working register, and then move the working register to the file ADCON1. That sets port A as digital input or output. Now we want to set port A as outputs. So we move the literal value of 00 hexadecimal to the working register, and move the working register to the file TRISA. Now, port A, bit 2 is used as the chip select 0 on the MC6821. Bit 1 of port A is used as register select 1. Bit 0 is used as register select 0 of the MC6821. Before we can set up port A, B, C, D, and E, we must switch to bank 1, because that is where the Tris A, Tris B, Tris C, Tris D, and Tris E registers reside. So we bank select TRISA, Tris A. Port B of the PIC16F877A is going to be our data bus to send data to the MC6821. Port C is used to control the 74HC245. Bit 1 is to control the direction of data on the 74HC245. Bit 0 is used as output enable, G bar of the 74HC245. Now port D only has one function according to our program, and that is the start switch input. That is the button we pushed to send AA hexadecimal or 55 hexadecimal across the data bus to the MC6821. Now here we move the literal of FF to the working register, and we move the working register to TRISD, T-R-I-S-D. I show zeros here, but they're all ones, which neither makes this nor there. You know, I could, let's do this. Let's change this to 0, 1, and that'll perform the same function. All of these bits right here will be outputs, and this bit, bit 1, or bit 0 for that fact, will be an input. Zeros are outputs, ones are inputs. So we've corrected that value right there. Port E. Here's port E. They're all outputs. So we move the literal to the working register, the value of 00 hex. We move the working register to tri-state E, T-R-I-S-E. Now, these 3 bits are used on port E. Bit 0, 1, 2. Bit 2 is used for the MC6821 reset bar. Bit 1 is used for the MC6821 read-write bar. Now, I replaced the MC68, this is bit 0. I've replaced bit 0, MC6821 E clock is no longer used. I replaced it with a 555 timer IC set to function in astable mode. So bit 0 of port E is no longer connected. Now, let's return to bank 0, where the registers port A, port B, port C, port D, and port E reside. So we bank select port A, and that puts us back into bank 0. Let's set up the MC6821 and the 74HC245 control bits. We're going to set reset bar high with bit set file, reset bar. And again, these labels were defined with the function hashtag define to set that label to that port bit, as we did at the very beginning there. Read write bar, we're going to set that high with bit set file. Read write bar, read write underscore bar. The chip select 0, we're going to set that high with bit set file, CS0. The register select 1 and register select 0. We're going to set RS1 low and RS0 high with bit clear file RS1 and bit set file RS0. Now for the 74HC245, the direction pin, we're going to set that high so that data flows from the A side, the 8 bits of the A side, to the 8 bits of the B side. And we're going to enable the outputs. We're going to pull that chip out of tri-state by setting G underscore bar with bit clear file G underscore bar. There are the control bits of our circuit set up. Now let's initialize the MC6821 for write to port A and write to port B. The first thing we must do is reset the registers of the MC6821. That sets everything to 0 inside that MC6821. So we go from a high to a low. Previously we had set reset bar high. Now we're going to bit clear file reset underscore bar. That's going to drive that pin low. We're going to have a little bit of a delay here called general purpose underscore delay. And now we're going to go high again on reset underscore bar with bit set file reset underscore bar. And that initializes the MC6821 to all zeros. Every register is set to 0. So we have a clean slate to work with. Now, we want to get to the data direction registers of A and B of the MC6821. So we're going to set bit 2 of the control register to 0. That will allow us access to the DDRA and the DDRB. So we move the literal of 00 to port B. We move the literal of 00 to the working register, and we move the working register to port B. Now, to select control register A, we set register select 1 to a logic low and register select 0 to a logic high with bit clear file RS1 and bit set file RS0. We toggle the read write pin on the MC6821. We call a delay. We bit clear file read write bar that writes this value up here of 00 to the control register A so that we clear that bit 2 to 0. We call another delay and we set read write bar high again with bit set file RW underscore bar. That takes care of the control register A. We have to do the same thing to the control register B. So we select the control register B by setting RS1 and RS0 high. That sets control register B to have access. Now remember, we have 0, 0 hex still applied to port B. So we're going to write that value with this routine right here. We're going to have a little bit of delay. call general purpose delay, bit clear file, read write underscore bar, so that the read write pin on the MC6821 goes low. We call the delay again, and then we set read write underscore bar to a logic high. The delays allow for the data to settle on that port. Now we set MC6821 port A and port B to output. In order to do that, we move the value of FF to the working register, and we move the working register to port B, the port B file. Move working register file, port B. Here we have set up the control register to allow us access to the data direction register by setting bit 2 in the control register A and control register B, bit 2 to 0. We had done that previously. Now we want to select data direction register A. So we set RS1 and RS0 both low with bit clear file RS1 and bit clear file RS0. And we are going to do the same thing with the read write. Call the delay, the general purpose delay, bit clear file, read write bar. That allows us a write to the MC6821. Call another delay and set the read write pin on the MC6821 high with bit set file read write bar. That takes care of setting port A to all outputs. Now if we set port A to 0, 0, then port A would be inputs. 0 is an input on that port of the MC6821, and 1 is an output. Did I get that right? I don't know, but y'all understand. So that takes care of the data direction register for port A. We go down here and we do the same thing for port B, the data direction register for port B. But this time, register select 1 is set high, and register select 0 is set low. And that puts us into the data direction register for port B. As long as bit 2 of the control register is set to 0. We have loaded port B of the microcontroller with FF back up here. So call our general purpose delay to let everything settle down. Bit clear file, the read write bar on the MC6821, that's read write bar pin, set low. Call another delay, and then set the read write pin of the MC6821 high with bit set file. Now we want to set the data bus to hex 04 to set bit 2 of the control register to 1 for access to the output registers A and output registers B. So we're going to set the control register of A and B bit 2 to a 1 again, whereas previously we had set it to a 0, so we'd have access to the data direction register. So we move the literal of 04 hex to the working register, and then we move the working register to the file of port B. We select the control registers for A with bit clear file, register select 1, that sets RS1 to 0, bit set file, RS0 to a high with bit set file. We write, with this little routine, the value of 04 hex into the control register A. We call our delay. We set the read-write pin on the MC6821 low. We have our delay again, and then we set read-write pin high again. And that places 04 hex into the control register A. Now we have to do the same thing for control register B. We bit set file RS1, that makes RS1 high, and bit set file RS0, that makes register select 0 high, so we have a 1 and a 1. And those pins are on the MC6821. And then we have to write 04 hex into control register B. We call our delay. We bit clear file, read write pin on the MC6821. Call our delay again, and then we set the read write pin on the MC6821 high again with bit set file, read write underscore bar. There we go. Now the MC6821 is set up to write to the LED circuits, and the PIC16F877A is set up to write to the MC6821. Shoo! That's a lot. So here we go. Here we go. Let's take a little bit of a break, and we'll come back and we'll finish this up. See you in a little bit. All right, I'm back. I got the front door opened up so we can air out the house before we have to hunker down for the winter time. It's going to be a cold winter this year. So, we've set up the PIC16F877A and the MC6821. Now let's drop into the program where all the action starts. We want to call a long general purpose delay, and I'll show you these subroutines at the end of the video. Now normally when the start switch is not pushed, it is pulled up, that pin input to the PIC16F877A is pulled up by a pull-up resistor to 5 volts. And so that input is high. So here we have an endless loop. When the input to that switch is high, bit test file skip if clear is not activated. It's not active because we're not clear, we're not low. So we drop into this go to, which brings us back to start underscore pause underscore low 0L. So we continue in this endless loop right here until that start underscore pause button is pushed. And then at that time, bit test file, skip if cleared, because we've gone low, we skip this command right here, and we jump into this point right here. Call long general purpose delay. Another delay. Now, we want to prevent switch debounce. And so as long as we're still holding that button low, we will bit test file, skip if set. We're not set yet. We haven't released the button. We're still low. So we go back up here, start pause, 0 high. And we continue that loop until we release the button and we're pulled up again by the pull-up resistor. So it's bit test file, skip if set. We jump over that go to. That's a neat way to alleviate that switch debounce. All mechanical switches have some bounce to it. Now, we're in the main part of the program loop. This is the beginning of the program. We want to send 10101010 to the MC6821. So the PIC microcontroller, the PiC16F877A, we move the literal hex AA to the working register, and we move that working register to the file port B. So now the port B, which is set up as our data bus, contains the value 10101010. We're going to move the value, hexadecimal value AA, which is 10101010 in binary, to port B of the PiC16F877A. And we do that by moving the literal AA, 0 little x AA, to the working register. And then we move the working register to the file port B. Now, we want to send that hexadecimal value, AA, to the output register of the M6821. So we bit clear file, register select 1. We bit clear file, register select 0. Now we, again, need to assert write low and then write high on the MC6821. So we call this delay general purpose delay. Then we bit clear file RW underscore bar, driving the read write pin on the MC6821. I'll get it right. We drive that pin low. We have another delay, and then we drive the read write bar pin high again. Bit set file RW underscore bar. Now we have to do the same thing with port B. We want to send the hexadecimal value AA to port B of the PiC16F877A. And then we are going to send that value that's residing on port B to the output register B of the M6821. I got it right that time. So we bit set file RS1, register select 1, we set that high, and we bit clear file, register select 0. We set that to logic low. And that, when we write that value into that register, it will show up on port B. And we do that by calling a delay to let everything settle down. We bit clear file the read-write pin of the MC6821, another delay, and we set the read-write pin of the MC6821 high again. And here we have a delay. And again, we stop until we have another button pressed. So as long as the pull-up resistor on that start switch is high, we go back to this point right here. Start pause 1L. Before it was 0L. Here we have 1L because we don't want to go way back up there. We want to stay down here. And then when the button is pressed, we jump over the go-to, bit test file, skip if clear. Now the button is pressed and it's pulled low, that pin input to the PiC16F877A is pulled low by the button press. We jump over the go-to and we have another call. And for switch debounced, we're still pressed low, so we go back, we're still pressed low, then we release the button, we bit test file, skip if set, because now we're pulled up, we're no longer low, we jump over the go-to, and here we perform the same process, except instead of AA, now it's 5-5. Now, AA was 1010, 1010, but 5-5 is 0101, 0101. And we're going to send that to the port A of the MC6821. So we bit clear file, register select 1, bit clear file, register select 0. So now we are sending that data out to port A after we write to the MC6821. So we have a delay to let everything settle down, bit clear file, the read-write pin of the MC6821, another delay, and the read-write pin of the MC6821 is set high. Now we have to do the same thing to port B of the MC6821. We move 55 to port B of the PiC16F877. And then we select where that data is going to go in that MC6821. So we bit set file, register select 1. We set the RS1 pin high. We set the RS0 pin low with bit clear file, RS0. And again, we pull the read-write pin low to initiate a write, and we set it high again. And that data, 0x55, hex, is written to port B. And we wait for that push button to release. and then we go back to main and repeat the process. Let's go back up there. We go back up here when all is finished. So here we have a button press, a button release, and we go back to main. And that's how you saw the LEDs move from 10, 10, 10, 10 to 01, 01, 01. 01? Let's go look at the subroutines real quick. This is let's do the long delay first. It's a little. We'll start up here. This is our general purpose delay, and this is our long delay. And the difference between the values is hexadecimal 0F and hexadecimal 0xFF. 0x, 0F, 0xFF. That would be hexadecimal 0F and hexadecimal FF. So what happens here, we drop into this, when we make a call to the GP underscore delay, we preload, we load the working register with 0F. And that's our load J counter with the loop count. And we move that working register to the file J. And I think that was SRAM location 20 hex inside the microcontroller. Now then we go down here to GP underscore load underscore K, and we load the SRAM location K with the same value 0F. Now we decrement GP underscore decrement underscore K. We decrement the K until it reaches the value 0. If it hasn't reached the value 0, then we go back up to this point right here, GP underscore DEK underscore K. We keep looping here until K is equal to 0. When it equals to 0, we jump over the go to and we decrement the J. Decrement file skipiv ZJ. So we go, if it's not equal to 0, then we go to GP load underscore K, which is right here. And we reload the K value with 0F, and we continue. When the J is equal to 0, we jump over the go-to that reloaded the K with 0F, and we return back to the call location. So that's how you create time delays in your program. The long general purpose delay, you can see up here we had 0F, but the long general purpose delay had FF. That's everything. I am absolutely certain after all of that I've forgotten something and left something out, but if I did, let's get back up to the top. If I did, y'all let me know. All right, folks, it took over a year here. 30 June 21, 1 July 21, when I ended this program. And okay, I'll provide links to the first two programs that show the circuit in action and the schematics of the circuit. I'll put bubbles up here and links in the description box below. All right, all. That I get really long-winded on this stuff. And I'm so sorry I did not put this up sooner. I should have put it up the week after July 21st there, but things kind of fell apart. We're barely back on our feet now. Oh well. Hope y'all's doing good. Enjoy the time with your family. And we'll see you next time.